meeting on Friday.
Oh, that's a lot. Wow.
Maybe.
Oh, my goodness.
I think 18, 19, and 20 are all kind of the same, like polarization. We have
Yeah, so, okay, so let's talk about polarization. So, we said that laser light is linearly polarized. Also, the light that comes from the screen of your laptop is also linearly polarized. And linear polarization means that the electric field vector is oscillating only along one line. So for Dell computers, usually the axis of polarization is vertical. For Apple computers, it is under 45 degrees like this. Usually it's not a rule, but this is what I have seen. And you need to know that if you have light that is not polarized, this means that for one very short instant, probably of the order of picoseconds or less, the electric field vector oscillates this way, let's say. The next picosecond, the next instant, the oscillation of the electric field vector is this way, later on, this way in the next moment. So on average, all directions of oscillations are equally probable. And we say that this light is not polarized, and usually the light around us is not polarized. It is like this. So if this unpolarized light has intensity, let's say S0, if you put a filter in front of it, a filter that is made of material that usually some long polymer molecules of this plastic material, oriented in the process of manufacturing, mostly along a single line, let's say this way. So a filter like this is going to absorb the light that is not, that is in any other direction, and it is only going to let out the light that is along the axis of polarization, along the transmission axis, so-called transmission axis, on the other side. In other words, here is this polarizer filter. You get unpolarized light in, and if the transmission axis of this filter, let's say, is this way, on the other side, you're going to get light that is going to be polarized exactly along the transmission axis. So completely polarized, linearly polarized light on this side. The intensity of that linearly polarized light is going to be exactly half of what it was before it reached the polarizer. So this is well, you can show it using some trigonometry, but for our purposes, this is all that you need to know. The polarizer reduces the light intensity by a factor of 2. Well, so now this light is not only reduced in intensity, but it is polarized, linearly polarized. If you place a second filter, polarizing filter like this, often called analyzer, let's say here is a second filter of the same type, and let's say that the axis of transmission of the second polarizing filter is this way. But look, the axis of polarization of the light that hits it is different. It is something like this way. let's say that the angle between the two directions is angle theta. In that case, it can be shown that after passing through the second filter, the light is going to have intensity reduced by a factor of cosine squared of the angle theta, the angle between the polarization axis of the light that hits it and the transmission axis of this second polarizer. So this rule, this result is called Malus's law. And you can keep going that way. For example, if you have a third filter, polarizing filter like this. So look, now, after the light passes here, it is now going to be polarized along the transmission axis of the last polarizer. So if you place another filter with transmission axis, let's say that is this way, while the light is this way, with angle, let's say theta prime between them, the light is going to have intensity reduced by another cosine squared. In this case, you're going to get, on this side, you're going to get, so the original is S naught divided by 2 times cosine squared of theta. It is going to get one more factor of cosine squared of another theta prime, in this case, and so on. So this is how Malus's law works, and this is the basis of answering questions like many of the questions here on the board. Yes.
So every time that we add a polarizer, you're just gonna add a cosine squared.
Exactly.
The angle is changing.
Exactly, that's correct, yes. The first polarizer though is reducing by a factor of 2, reducing intensity by a factor of 2. If the incoming light is not polarized. So knowing this, let's look at some homework problems. Let's see. So let's start with problems that are the same type like what we said so far. Maybe, let's see. Okay, let's do problem number 18 maybe. Problem number 18 from the homework assignment on chapter 24. Let's see, what is it? So you have unpolarized light with given intensity, for my version 1.6 watts per square meter. And it is incident on a polarizer with transmission axis that is vertical, from what I see here. And after that, you have another filter called analyzer that is with transmission axis at some angle, I guess. Well, so the answer to question A is going to be the incoming intensity divided by 2. So for my version, the incoming intensity is 1.6. After the first polarizer, you're going to have intensity half of 1.6, 0.8, right? This is the rule. We don't prove that formula. We just use it because trigonometry is not a requirement for this course. Part B, after that, you have a second filter called analyzer at 75-degree angle with respect to the transmission axis of the first polarizer. what is the intensity that reaches? Well, you started with intensity S naught divided by 2, right? This is, and you are going to cut it by another factor of cosine squared of the angle theta. Yes.
So when we're doing these calculations, no matter how many like filters it goes through, we're always gonna use the S naught instead of like the intensity that's created by going through the polarizer.
Well, it depends upon what they're asking and what they're giving. So they're saying initially S naught is 1.6. Part A, it is going to be half of 1.6. Part B, whatever is left, which is S naught divided by 2, is cut by another factor of cosine squared of 75 in this case. So just look at the examples, and depending upon the context, and depending upon what you define as S naught. For this problem, S naught is defined as 1.6 watts per square meter. The answer to part A is S naught divided by 2. The answer to part B is whatever hit the last analyzer, the analyzer, multiplied by cosine squared. So whatever hits the last, the filter, the polarizing filter. So it just has to be read carefully, and it's difficult to make a mistake here. Okay, other remarks here about this? So when you're answering the homework questions, make sure that you square the cosine, and make sure also that your calculator is working in degree rather than in radians, because in this chapter they use degree mostly. Okay, so the next question is a similar question. Let's see, question number 19. So you have again a combination of polarizer, analyzer, but now they want you to find the angle between the transmission axis. So let's see, problem number 19. So you have unpolarized light. After that, you have the polarizer. And after that, you have analyzer that cuts the intensity by 78.3%. Determine the angle between the transmission axis. Well, let's see. So look, 78% of the light falling on the analyzer. So 78% from reduction from here to here. So basically they tell you this. The light is already polarized, so you don't need to do halving here because nobody is saying anything about that. But basically, you set up the equation like this. You have certain polarized light with intensity AS after the polarizer, and after the analyzer, you're going to have S multiplied by cosine of the angle that they give you squared, I guess. In other words, this last intensity S prime is what they say that this number is absorbed. Therefore, the number that is the intensity that is transmitted is going to be 100% minus what they say here. In this case, it is going to be 21.7%. So this is going to be 21.7% of whatever was S. In other words, they say that S prime divided by S is equal to 0.217, but it is also equal to cosine squared of the angle that you're looking for. In other words, cosine of the angle is equal to square root of 0.217. And therefore, the angle itself is equal to inverse cosine of the number that 217. So this should be the answer for my version of the problem. So notice the tricky part here is that they don't tell you what is the transmitted intensity. They tell you the percentage that is absorbed, that is not transmitted. So you have to fill in to 100% to figure out how much actually is transmitted. In other words, just plugging numbers in formulas not going to work. You have to use a little bit. You have to read the problem basically carefully. Okay, questions and remarks here? So for my version, the answer is 62.2 degree. Hopefully, yeah, it should work. Thanks now. Yep. Okay. If no questions, let's go to the next problem. Again, a similar problem, but now you have three filters. The first one is going to cut the intensity by half, the second one by cosine of theta, and the third one by another cosine of some other angle. And the trick in this problem is that they don't give you the angle between the transmission axis of the insert and the transmission axis of the analyzer, the last filter. They don't give that angle directly, and they're trying to trick you, of course. So, okay, so just answer this the following way. So the intensity that is eventually going to reach the photocell is going to be, well, you start with original S naught. For me, S naught is 155 watts per square meter. The first polarizer is doing a factor of 2 reduction of intensity. The insert is doing cosine squared of angle theta for me, whatever angle theta for me. Whatever, and the angle theta is 29.7. So you have to do cosine squared of 29.7 degrees. See? And after that, you have another analyzer. And if you carefully look at the diagram, the transmission axis of the last filter is horizontal. So you have to figure out the angle between this horizontal transmission axis and this red line, which is the direction of polarization after the insert. Well, if this is theta, the angle between the red line and the horizontal is going to be 90 minus theta. And therefore, you're going to have a factor of cosine squared of 90 minus 29.7 minus degree. And this should give the trick. It should give the answer for the intensity that eventually hits the sensor. Okay. Any questions, remarks? Okay, so we did 18, 19, 20. Let's see what is problem. Let me see which problem we can do. Okay, let's do problem number 13. So problem number 13. So you have a laser with intensity that is given. It is quite intense laser beam. RMS value, so average intensity is given. Find the RMS value of the electric field and the magnetic field. And look, you just have to use what we proved last time. The intensity of light is expressible in several different ways. For example, it can be expressed in terms of, so in general, it is energy density multiplied by the speed of light. But energy density can be expressed either as 1 divided by epsilon naught E RMS squared, times C again, or it can be expressed as, I'm sorry, I'm correcting this. It is epsilon naught times E squared rather than, or it could be 1 divided by mu naught times B RMS squared. Of course, everything is multiplied by C. So one of those two ways, you're given as, you know the value of electric permittivity of vacuum or air. You know the value of the speed of light. You can solve for electric fields. So, for example, if you use this, your answer to part A is going to be like this. E squared RMS is going to be equal to S divided by epsilon naught and divided by C. And in order to get the electric field itself, RMS value, you have to take square root of that. In a similar manner, the magnetic field squared RMS is going to be equal to mu naught times S divided by C. And again, you have to take square root to find magnetic field. And of course, the units for electric field are newtons per coulomb, and for magnetic field, the units Tesla. Okay, remarks, questions? If not, let's do the last problem here on this list. Last problem is problem number 16. Problem number 16. So you have electromagnetic wave that hits, that has a value, they give you the value of the magnetic field, RMS value, and they say that this wave is going through open window with given area, and they ask you how much energy goes to this window in 55 seconds. And look, you just have to use the definitions. So the intensity, since they give you the magnetic field RMS value, you have to use the second formula for intensity. So is 1 divided by mu naught magnetic field RMS value squared multiplied by the speed of light. But intensity is defined as energy that goes through area perpendicular to direction of propagation per unit time t. So this is the definition. So you see the left-hand sides are intensity. The right-hand sides have to be equal to. So you have energy divided by the area that they have given and divided by the time that they have given has to be equal to 1 divided by mu naught times p RMS squared times the speed of light. And therefore, just the energy is going to be equal to area multiplied by time multiplied by 1 over mu naught times B RMS squared. And they give you everything. They give you the area, the time, mu naught is a constant, B RMS is given, and the speed of light is also given. So you have to substitute the numbers and you should get the answer. Okay, done with the homework. So you can finish the assignment and you don't need to worry during the break for homework assignments. Now let me, so I was planning to start chapter 25. But before going to chapter 25, let's look at the following situation. So here is let's turn off this projector. And let me turn on this light. So now you have light with some intensity, and you see that intensity is, of course, brightness. And here is a polarizing material, a polarizing lens. They say that the transmission axis is this way. Somebody has figured out the transmission axis this way. Okay, so what is the intensity? You see that the intensity drops after I put the filter. What is the intensity now compared with the intensity now? Original intensity this, after the polarizer intensity is what? Half, exactly half. And the light that hits now the screen is polarized along the transmission axis of this filter. So take this polarized light. Yeah. Okay, let me use a different polarizer that is going to fit better, just bigger. So now half intensity. And now start with the analyzer. Look. And you notice it, but if we turn off the lights completely, look. So you start Well, let me show some conceptual questions, but keep in mind that for those conceptual questions, some of the answers that are